Y'all might have seen this fancy 3D badge that's been floating around on Twitter and the like. It's for part of the Vercel ship event. And they tend to go a little all out with these super fancy 3D physics-enabled virtual environments. They've done these for the last few events, and every time they've blown me away. This is one of the first times that they've actually documented how it works. I have a bit of inside info on here because I've been keeping an eye on the particular developer who enables a lot of this, but never did I expect him to write a blog post about how and why they do this. For those who aren't familiar, the engineer is Paul Henschel. You might know him under his Twitter handle, 0xCA0A. He's an absolute legend. He's the creator of React 3 Fiber, of Zustand, of the entire Poimanders org. Genius React dev, possibly knows React better than anyone on the core team. One of my favorite humans. I've looked at him forever, and getting to read anything from him is an honor. So I am very hyped to get to see why and how he built that badge. Specifically, how he did such using React. So let's get started. Building an interactive 3D event badge with React 3 Fiber. In this post, we'll look at how we made the dropping lanyard from Vercel Ship 2024 site, diving into the inspiration, tech stack, and code behind it. I didn't showcase this, but when you load the page, it just kind of drops in once it loads, and it's really nice. It looks even better on the site. I highly recommend checking it out. On here, you're only going to see 30 FPS because I record at 30. Inspiration. We've shared digital tickets for event attendance in the past, but this time we wanted to make it one step further by creating a tangible experience. When Studio Basement made a video in Blender that depicted a virtual badge dropping down, we liked the idea of it so much that we started to wonder whether we could make it interactive and also run it in the browser. Ultimately, we wanted a highly shareable element that rewards the user for signing up and makes it worth their time. Here's a little video of it with Guillermo's badge. And it is very rewarding. Like once you've signed up, not just getting like some spam email, but actually getting a physical thing you can move around is really cool. So what's the stack? To accomplish this task, we chose the following tech. Blender, to prepare and optimize the original models for the web. React and React 3 Fiber, which is a reactive declarative renderer for 3JS. Dre, an ecosystem of components and helpers for 3JS space stuff inside of React. React 3 Rapier, a declarative physics library based on the DimForge Rapier physics engine. Really cool stuff. Like Rapier is incredible, and seeing that they're now putting it into React, super cool. I didn't even know this was a thing. It's been around for a bit too. Damn, throw that a star so fast. Good old Poimanders, always killing it. Then we got Meshline, which is a shader-based thick line implementation. I'm assuming that's for the lanyard part. We'll see though. While some of the concepts we're about to cover may not look familiar, don't let them overwhelm you. The implementation is about 80 lines of mostly declarative code with a sprinkle of math. Check out the sandbox first to get an idea. Ooh. That's so cool and simple. Can I open this up? Oh yeah, this is just Code Sandbox. I've said this a bunch, but Paul Henschel goes so out of his way to make sure all this stuff runs in simple sandboxes. That's all the code for this. That's actually so cool. And I promise you, on my 120 hertz monitor right here, this looks insanely smooth. So let's actually take a look at this code quick before we go too much further in the article. We're importing 3, of course. Use ref and use state from React. Canvas, extend, use 3, and use frame from Fiber. Ball collision, cuboid collider, physics, and a bunch of like physics and rope stuff from Rapier. Meshline geometry and material from Meshline. Interesting. We wrap the whole thing in Canvas, obviously, because that's the whole point. Physics is a wrapper, and this came from Rapier. Figured as much. Cool. So the physics come from the Rapier library. Even has a debug flag enabled. How cool is it that you just enable a debug flag in your physics by passing it as a prop? Gravity, so you can actually change the gravity levels. I bet I could change this to be like -10, and now it's going to be way floatier. Oh, it's going to fork the sandbox to my drafts. That's what it's going to do. You see how much floatier it is? Or I can make it like 100. And now it flops way harder. How cool is that? You can even add gravity to the sides. So if I do that, it's going to go forwards. And since it's React, this is all hot reloading, which is so cool. This shit, like I could just nerd out about React 3 Fiber and hot reloading with physics engines forever. This shit's so cool. But we're here to read about how they made this, not just playing with the code. Building a rough draft. The basic imports we need to resolve around our canvas, physics, and the thick line for the lanyard are as follows. Yeah, look at that. The stuff we just read. Very simple. In order to use the Meshline library, which is vanilla 3JS in React, we need to extend it. The extend function extends React 3 Fiber's catalog of known JSX elements. Components added this way can then be referenced in the scene graph using camel casing, similar to native primitives like mesh. Interesting. So once you've done this, you can just call Meshline geometry wherever. Makes sense. Setting up the canvas. Now we can set up a basic canvas. We need React 3 Fiber's canvas component, which is a doorway into declarative 3. We also added a physics provider, which allows us to tie shapes to physics. In Rapier, this is called a rigid body. With this, we have everything we need. Yep. We just have a canvas, which is where everything goes. We then have the physics, which means everything below this now has access to physics. And you just do the things. I know game devs might get a little mad looking at this, but React devs looking to make 3D stuff, how cool is that our React knowledge of declarative design just works in 3D now? Magic. The band component. Just a little phallic. I'm sure that Prime's audience is loving this. Now let's make the band happen. We need a couple of references to access them later on. The canvas size is important for Meshline, and the 3JS catmull rom curve 3, we're officially out of my pay grade, helps us calculate a smooth curve with just a few points. We only need 4 points for the physics joints. The band, the fixed location, and then the 3 joints, all just using refs. If you're curious why refs, we don't want the whole component to re-render every time any of these points changes. And by making them refs, they still live with this component, but don't trigger re-renders when they change. That way we can trigger canvas changes without having to re-render the component. Re-renders only happen on state changes, which allows you to not eat the cost of React renders while using React for your 3D stuff. Here we have the canvas size, which we get from 3 itself. And then we have the curve, which comes from the state call where we create the curve with these values. So now I have to actually define these joints. The joint is a physics constraint that tells the engine how shapes interact with one another. We'll now start to connect the joints, and we'll later define a fixed rigid body that cannot move. We hang the first joint on the use rope joint the Rapier provides. There's a lot of different constraints for rotations, distances, etc. The other joints will hang on each other. Basically, we will have made a chain that hangs on a fixed point. Use rope joint requires 2 rigid body references. One is the 2 anchor points for each, which are 0, 0, 0, which is the center, as well as a length, which is in this case 1. So these are the 2 bodies that they're creating. It's like the start point and then the length they want it to be. And they're passing it the fixed start point, J1, these references, and then the length. They're doing that for all 3 to create these 3 chunks of the rope. So now let's actually create a curve. Rapier will now move the joints along an invisible rope, and we can feed our catmull rom curve the positions of these joints. We let it make a smooth, interpolated curve with 32 points, and then we forward that to the mesh line. We do this at runtime at 60 or 120 FPS, depending on the monitor's refresh rate. As I said, check out the demo yourselves. I'll leave the link in the description because on your monitor, it'll look even smoother than it is in this video, which is only going to be at 30 FPS. React 3 Fiber gives us an out to handle frame-based animations with the use frame hook. Again, the more you can do your compute without updating React state, the better. And here, they're just updating the locations of things on the curve every frame without having to run a re-render. If you threw a state call in here where you're updating the state, then you're going to be rerunning React on every frame. But when you use the use frame hook, that can run in the background and not affect React. So let's talk about the view. Now we need the view. It consists of the fixed rigid body, type equals fixed, 3 rigid bodies for the joints, which are J1, J2, and J3, as well as the mesh line that we extended above. The joints are positioned in a way that makes them fall down with a single swing. Yeah, here we have the top rigid body, then we have the 3 for those chunks of the rope, and we can see the ref is bound here so that we know what properties that rigid body should have. And now these components can handle everything themselves in the background without causing React to re-render. Again, in some ways, we're opting out of React's state model and data model, but we're doing that in order to still get their composition model and their declarative model so that the code is just as easy to write and think about, even if we're manually avoiding re-renders wherever we can. Now for the card component, which is the part here that can spin around. It pulls the whole object down. There's a lot of interesting things that are going to be fun to get right there. And that's all it's missing. All it's missing is the interactive card, which we need to attach at the end of the last joint. For this, we need a new reference, some variables for math, a state for dragging, and a new joint. This time, we'll use a spherical joint so the card is able to rotate. So we create all these vectors for the angle, the rotation, the direction. Interesting. We're actually using these, not here. We do create a spherical joint with the hook. It's crazy just calling a hook to create joints that attach things. You pass it the references for the 2 things being attached, and then the points on each in which you want that joint to be bound. Rapier defines a few rigid body types. Fixed, which isn't affected by anything. Dynamic, which is the default, which reacts to any other rigid body. As well as kinematic position, which is the position controlled by the user, not the engine. The card needs to be kinematic when dragged and dynamic when it's not. We will later use pointer events to set the dragged state. Interesting. So this is effectively, we want to turn off the physics when the user is dragging. We want to re-enable it when they're not. So the previous use frame code now changes. If dragged, then we set the pointer location to be wherever we're currently putting the pointer. We set the vector's location to be wherever the pointer is. And we unproject the camera. Not necessarily sure what that is for. Hopefully we'll figure out a bit more in a bit. We copy the vector and the camera position and we normalize them. We then add the scalar based on the camera's position. And then we set the next kinematic translation, which is like the inertia based on what we have done there in our drag. And then we calculate the current curves and where the band should be for everything else, because you can't drag the band. You can only drag the card, if I recall. Yeah, you can't drag the band. So the band has its own everything, and then the card is a result of that. When I drag this, now the card can't move by itself, but the band has to follow. So they still have to update the band's location, even if the card's location isn't being updated by the physics. And then as soon as I let go, the physics takes back over. And if I like swing that way, it holds the inertia from the movement because it's still doing the inertia calculations. It's just not applying the difference. Very interesting. So we calculate the curve, and then we tilt the card back towards the screen. Calculating the drag state is the complicated bit of the code. Without going into too much detail, if you want to translate pointer events to coordinate a 3D object, this is called a camera unprojection. 3GS has a method for this, unproject, which does most of the math. Interesting. The obtained vector gets applied as a kinematic translation. We move the card with the mouse and trackpad, and the lanyard joints will follow where it goes. Yep. Another hard nut to crack is that we allow the card to rotate, but we want it to always rotate from the back to the front, which is not physically accurate, of course, but the experience would suffer otherwise. Yeah, they always want the card to be facing you. So even if you get it to rotate, you want it to eventually resolve back to facing you. I did notice that there was a little bit of code here with the set angle. I'm assuming that's what it is. To solve this, we use the current rotational velocity, card.current.angvel, in the rotation, which is the current rotation, and they spin the y-axis towards the front. Yeah, so they have the x angle, the y angle, and they subtract the rotation. So they're constantly slowly setting it towards you in increments of like 0.25 times the current rotation. Very interesting. So what about the card's rigid body and pointer events? We use a cuboid collider, which is a box shape, for the card. Then we drop a mesh inside that will move along with the rigid body. This mesh will later be exchanged with the Blender model. There. This lets you work on something initially and then drop in a real model later. If you know anything about game dev, it's that you don't use actual models when you're doing dev. You have random boxes, like texture errors. What's the classic like source texture error? The pink and black I'm thinking of. This is when you're making the game. You're not necessarily using these. You might just have like blank empty textures when you're working, but most devs don't work with the main models when they're figuring out stuff. But as long as you know how to drop in your Blender model or wherever else you're getting it from later, totally fine. Just cool seeing these real game dev patterns finding their way on the web too. The pointer events for up and down set the drag state. On the down point, we grab the current point of the model, e.point, and we subtract the card's position in space, which is the card current translation. We need this offset for the use frame above to calculate the correct kinematic position, which is this guy. Cuboid collider, the mesh, we have these drag calls for pointer up, pointer down. All checks out. And also the type where we change it from kinematic position to dynamic when it's being dragged. So adding the dynamic name. We wanted the card to display the name of the user dynamically. To achieve that, we created a new scene that renders the user's name alongside a base texture. Then we'll use Dre's render texture component to render that scene into a texture. We start by creating a scene that renders the base of the badge texture. So here's the mesh that is the standard like texture, which has the ship and all the other stuff. We have the badge texture, but we're still missing the name. We'll add it to the scene using Dre's text 3D component. Text 3D is nuts. The fact that you can 3D render text on an object and have it transform properly is so cool. So text 3D, we're rendering the font. We're actually embedding the font via the Geist regular JSON file. Fascinating. And then we just drop that as the child, and it works. Same thing with the last name. You can even apply different properties. So here we lowered the position, so there's enough room for it. Since this first one is the first name, we want this to be below. We don't got Flexbox here, so we got to manually position our shit. Also love the math.py for the rotations. That's how you know you're deep. This is an entirely different scene. We want to add the result of the render into our badge as a color. We achieve this using the render texture component, which will render our scene into a texture that we can attach to the mesh map. So here we have the mesh geometry is node card geometry, mesh physical material, and then here we render the texture and the badge texture all as children of the mesh physical component. Again, how cool is it that we have a mesh component that we pass children that are our textures and they render and behave how we want them to? Let's talk about the finishing touches now. the things that make this as nice as it is. We have everything in place now. The basic meshes are quickly changed out for the Blender models, and with a little bit of tweaking in math, we make the simulation more stable and less shaky. Here's the sandbox we use to prototype the component for the ship site. As per usual, Paul provides a sandbox for you to go play if you want to. That's really handy. Went from holding our hands to saying, good luck, have fun. Yeah, here's the preloaded assets. I'm coming from Contentful, funny enough. It is interesting that all the text calls are gone. Very interesting. Usually once you're deep in Paul code, what you end up finding is there's a ton of weird external assets that have been optimized, as well as a ton of lighting calls. The amount of effort he puts into lighting is surreal, but it gives that vibe to all the stuff he makes, where it really feels like you're reaching into a 3D world. Even in his like simple demos, he tends to go out of his way with the lighting, and it shows. Like the way this looks and the way things reflect is just so good. Yeah, I'm impressed. Curious what you guys feel though, because this is some weird 3D deep dive stuff, and I know a lot of y'all are just web devs, but is this cool to you? Because I know it's really cool to me. Let me know in the comments if you want to see more crazy 3D and React 3 Fiber stuff. Until next time, peace nerds.